Now, finally, there's something I'd like to say about converging sequences that's going to be useful later. Suppose that we go back to our example of looking at sequences or objects that occur in two-dimensional real space. And let's suppose also that there is some set of this space, some part of it that is defined in this way. First of all, it has no holes. Second, the edges are included in the set. And now, into this space, let's put our sequence Z. So here is Z0, Z1, and so on. And on goes our sequence. What's important for what I want to say here is that suppose there is some space like the one I described, a subspace rather, that's a subset of the broader set in which this sequence exists, such that once you know that the sequence is in there, it won't leave. Second, suppose this sequence has a Cauchy property. That means that it's going to converge to something if this is a complete set, which of course it is in this case. That means that for sure, the Z star to which this Cauchy sequence converges has to be in this set. It makes sense. The distances between the different objects, the different elements of the sequence are getting smaller. And since the Cauchy property is satisfied, that means that there is also something that they are converging to. And the edges of this set are included. And that means that either they have to converge to something in the set, or they have to converge to the edge because they can't go outside it. That would violate the idea that every element of the sequence has a smaller and smaller and smaller distance between each of the elements. And while this picture is describing this phenomenon for the case of two-dimensional real space, this, of course, is going to be true of any relevant space. And in particular, it's going to be true of the space of the bounded and continuous functions, which is what we're interested in right now.